All right, welcome everyone back to our course, Introduction to AI, Neural Nets, LLMs, and Generative AI. In this course, just to review, we have covered various aspects of the neural network. We have covered the fact that they are universal approximators. We covered what we understand about neural networks and aspects of the neural networks that still elude or escape our understanding. So it's a very interesting thing. Every other algorithm we feel we know, but with neural networks, it's a bit of a mystery. As we scale it up, we understand some parts of it, but not others. The parts that we do understand, this course, of course, goes into. And last time we covered gradient descent. It was a bit of a heavy topic. Today's topic is activation functions. And we will also do another topic, backpropagation. Activation functions and backpropagation are the two key topics for today. On the practical side, now it's time to get heavy onto the practical side, into the labs. So today, I release for you your very first homework to do. Now, please do that, these labs. The teaching assistants will help you through with this. It's a straightforward lab. It is both straightforward and not straightforward. You'll be able to make quite a bit of progress on your own. You'll probably not be able to solve the problem completely or to complete satisfaction till the end of this course. It's a little tricky, but that's the whole point. We'll use this problem set as a backdrop on which we'll cast new ideas as this course progresses. Any questions before we move forward? All right, folks. So in that case, and are you, please be aware, I'll just give you a walk through the course portal. I hope you're aware that your textbooks, everything is listed here. If you are not on Zoom, perhaps a bit late, but go click on the Slack invite link, let us know. We'll add you to the course. Today, I have updated the material for activation functions. I'll just quickly go through the course portal. You should see for the notes on activation function, there are some notes that I have created. So you should look into those notes. A very short summary of some of the more important activation functions. So this is part of your study material. And other than that, let's go back to activation functions. There are activation functions that are there in the most dominant deep learning library or neural network library, which is PyTorch. It's good to see it. You'll see that there's a pretty large catalog of activation functions. And you will take some time to gradually acquaint yourself to it. Today, I'll introduce you to them. I have talked about it in the past. I'll talk about it a bit more today. Then there is a very nice Jupyter notebook, which I encourage you to study, created, which shows or visualizes these activation functions. Today, we are going to cover some of this in the class. You will see what they are, right, and how they work. Just a few of these will do. So that's for today. Then there is a pretty good survey. Some researchers took the time and the pain to curate a comprehensive survey of 400 activation functions. It should speak to the richness of activation functions used in neural networks. Why do we need so many different kinds of activation function? Because for every problem, something else may work best. And in machine learning, there are parts of the problem you can solve and part of the problem that you experiment and figure out empirically, which is best. Right? So which activation function is best for your problem? You only figure out by trying it out. There's a lot of experimentation and hacking. And it also goes to the heart of what I mentioned about neural networks. We understand some part of it, not all of it. Right? So why is it like, why can't we just look at a problem and say, this is the activation function to use? Answer is, we don't understand it yet. PyTorch today is a dominant library, and I will talk about it. I'm just giving you a quick overview. PyTorch is the dominant Python library to write neural networks in. We are going to learn to write neural networks from scratch. You folks already have my lab. You must have noticed that I created neural networks from scratch in those. And it was done using PyTorch. But today, I will talk about PyTorch in greater detail. Now, I've released a homework which should keep you entertained. It's a very basic homework. If you just get started with PyTorch today, you should be able to finish it before the weekend comes or during the weekend. There's a PyTorch website, which you can go to. This is the PyTorch website. Go there, install PyTorch, put in your hardware configuration. It will tell you how to install PyTorch. Like, for example, this would be my machine configuration on Linux. So then this is what I would do to install PyTorch. So install the PyTorch, and in the PyTorch, do you notice that, by the way, PyTorch is it is not just a dominant library. It is the dominant library. Almost everybody writes today the neural network code using PyTorch. If you look at GitHub, for example, it has 76,000 stars. There are 20,000 forks that have been made on it, and so on and so forth. So get started. It is very well documented. You see the tutorials here. And this is what we should do. Today we'll walk through some of the basic tutorials and examples in this course. So really worth getting into, but at the same time, there's extensive document. PyTorch has spawned a whole ecosystem of sub-projects or other projects around it. So if you want to do natural language processing, for example, there is PyTorch text. You want to do audio processing, there's the audio. Computer vision, there is the vision. Arrow is for the data format. PyTorch data recommender systems is here. You want to do inference server, you can use torch serve, again, a work in progress at this moment. And XLA devices is like the Intel devices and how to accelerate it on those. And when you look at it, that is only a small list of projects that have formed around PyTorch. Graph neural networks, a very important topic, has led to its own ecosystem of projects around PyTorch. So there are lots and lots of sort of projects that are happening almost every day around this technology. So it's a vast ecosystem. Now is a good time to get started with it. Right? So please do get started with this and spend some time every week playing with this technology, writing code with it, and so forth. There is also...
It's a paid application.
Come again?
This is the paid version.
Oh, no, there is no paid version for this. It's completely free. Yeah, completely free. And it was released by Facebook. They make a massive amount of sponsorship for this, right? But it is open source, completely open source. Okay. Now, there's also a YouTube. Those of you who are visually inclined in learning, I highly recommend that you watch the videos. Like if you prefer, you learn faster from videos, micro-learning format, small 10 minutes, 20-minute videos, then by all means, learn from the videos. Right? There are lots of videos here. PyTorch beginner series in particular is very good. Half an hour each, give or take. So that's an excellent resource. Now, one more thing that is optional that we will cover is called Lightning. PyTorch Lightning is a framework that makes writing PyTorch code easier. I don't want you to get started with PyTorch Lightning immediately. Today we'll write code without PyTorch Lightning. But what PyTorch Lightning does is Once you get familiar with PyTorch and you know how it works, then you can use PyTorch Lightning as yet another framework on top of PyTorch, and it takes the boilerplate away. It takes the obvious away. It not just only does that, but it actually makes it much easier to work with your GPU. Like, for example, you run your code, it will figure it out. If you have a GPU, it will automatically do the acceleration on the GPU. As you know, in deep learning, having a GPU makes a world of difference. Right? I'll give you an example. There is a task that I was trying to do, and I forgot to turn on the GPU enablement. Next morning, when I came back, it was still running. I killed it. I mounted the task on the GPU hardware, and it finished in a few minutes. Okay? So that's the difference between running it on the CPU and a GPU. You must do that. Also, running it on GPU is easy. Most people remember to do that. And now PyTorch itself has native support for accelerate and gives you, even if you forget to do that, you can set some baseline configuration so that it loads it onto the GPU. And more importantly, when you have multiple GPUs in your server, many of them, then it is a lot easier to use something like PyTorch Lightning, because it will automatically do a distributed multi-node compute of your code. Right? Now, those of you who have any experience with systems programming and distributed computing, you know that doing it by hand is quite a pain. It is far better to do it using a framework that can facilitate that. Right? So that's the another topic we'll cover today. The next topic we'll cover, which is the main topic for today, is the backpropagation. So while your minds are fresh, I'll actually start with backpropagation. Go ahead.
What's the difference between JAX and PyTorch?
What's the difference between JAX and PyTorch?
You know why I'm asking you.
Yeah. All right, that's a very good question. So it turns out that PyTorch is not the only kid on the block. Right? There are some competitors. The older one was TensorFlow, which came from Google, which is an interesting history. Google used to have something inside. And then they said, okay, we need to do a clean implementation and do something, and let's do it in the open source. And so they released TensorFlow, which was the clean TensorFlow 1.0, which was the clean, proper implementation of deep learning library. It took the world by storm, because everything that came before it was rather crafty. It was meant for researchers, like the cafe and all of that. Researchers were using it, and they were a bit hard to use. So TensorFlow was a great, great improvement. It had an immediate adoption. Well, good news, bad news. Good news is that you had something very rock solid. Bad news is people realize that it is almost like coming to a bicycle race and being told, okay, here are the parts, first build your bicycle. Right. So it was sort of low level, and it made the whole execution a bit problematic. And there's some technical details. What you had to do is you have to describe your execution graph as a static graph, and then you had to compile it, and then you had to execute it. And so, because there was no dynamic sort of execution graph created, it was a little hard to put breakpoints and debug. And imagine taking the debugger and the ability to put any breakpoints away from developers. It's just a bit much harder. You're left to just putting traces and so forth.
It was arrogance from the developers also.
Yeah, Sachin says there was arrogance from the
They did not listen to the community.
That too is true. Yeah, that is true. And so what happened is that so as a revolt to that, as a rebellion, two things happened. One, a brilliant fellow created the Keras library, which put some sanity on top of TensorFlow, made it very easy to use, very logical to use, and easy to get started. And then Facebook came up with an alternative framework, PyTorch, which was very Pythonic. TensorFlow still, because see, all of these libraries are ultimately implemented in C, C++. Right? So the Python is just a layer on top of it. TensorFlow never really felt Pythonic, whereas PyTorch became a very Pythonic. But even when it is done, what happens is that, why do you use these libraries? I talked about the fact that, and I will talk about it today, they have a quality called auto differentiation or AutoGrad. Right? These frameworks differ from normal numerical libraries like NumPy or any, like for example, you can write your own code to compute the value of a function. Right? So write a simple function in any language you want, give it the input, you can find the output, implement the output. The difference is these libraries, whenever you define a function and so forth, they're capable of finding, not just evaluating the function, but they're capable of evaluating its derivatives also. Right? So these are auto-differentiating frameworks. And it's a big deal because neural networks, as you will learn today, run on derivatives. Derivatives is the workhorse. I have been speaking about gradient descent. What was the gradient? It was the derivative. Right? Learning is with the derivative. Inference is in the forward pass. Right? FX, if you think of the entire neural network as a function, then the forward pass, giving it input, getting an output, the inference is just the evaluation of the function. Right? The learning part is the gradient descent. That needs the gradient of the function. And so derivatives matter. So PyTorch did an amazing job, and soon it came late to the party, but it pretty much won the mind share and the hearts of all the researchers and the people. So even today, for example, TensorFlow runs on more devices. I believe its support on mobile devices is better. PyTorch is still in the catch-up mode. Right? The inference part of it, of TensorFlow, still goes strong. You can do good inferences. And yet people, despite its a greater maturity, people always prefer using PyTorch for a reason. Keras came, and by the way, then TensorFlow 2.0 was based on Keras. But the Keras had a problem, and TensorFlow 2.0 had a problem. While TensorFlow 1.0 was very low level, TensorFlow 2.0, Keras based, is too high level. Researchers wanted something in which it wasn't that easy. I mean, it's okay. This Keras is very easy. You can describe a neural network in a couple of lines. But if you want to see what's going on inside, it becomes soon a little bit intractable. Right? So people wanted something that was easy enough, and still you could see what was happening, and you could put your finger into it, right, and take a pulse of the thing. Right? And so PyTorch seems to have hit that sweet spot. So then the question is, well, it's one kid on the block. People realize, and every framework that succeeds, then people learn from it, they look at its deficiency and start creating a new framework. So JAX started out again as a different framework. They said that, see, we are building all of these things over libraries that are somewhat dated and has been growing for a long time. Let's create a completely new auto-differentiating framework, much more tighter, much more core optimized. So that's when they started the JAX project. And Google has now almost completely gone behind the JAX project. Right? So JAX project is doing quite well. And if you notice, if you will look at the industry, you will find that Google is now often releasing code in JAX, even though they are the owners of the TensorFlow open source project, pretty much the big sponsors of it. Right? So that Hamad, is the answer to your question, the JAX part. But JAX is not the only new kid, the new David against the Goliaths. There's also the TinyGrad, yet another framework called TinyGrad. And TinyGrad takes a very interesting approach. It says, what if we could start with the hardware and vertically integrate up? The problem with PyTorch is that PyTorch now compiles to CUDA on the NVIDIA GPU. And CUDA is a black box. God knows what they do up there. But basically, inside that, when you look at the GPU, they have their processing units, they have their cache, and then they have their resident memory, which is the HBI, high bandwidth memory. Then data gets loaded into the high bandwidth memory. But what happens is when you do the matrix computation, blocks of data are being swapped in and out of the processing core. Right? And a lot of the complicated things are happening. TinyGrad's approach was, can we start all over again? Right? A PyTorch is easy, we can do that, but at some level, it sort of says, we'll stop here and we'll hand it over to CUDA, and then CUDA will transpile it for their hardware, the NVIDIA hardware, and then execute it. So TinyGrad's ambition is to create a vertically integrated hardware software, no boundaries thing. And so they have started, and they have hardware ambitions. So it's the first open source project that wants to do some, and it has many other advantages. See, every open source project has its pluses and minuses. Right? In this course, we'll standardize on PyTorch simply because it is by far the de facto standard today. If you go to Hugging Face, you'll see that of the close to 500,000 models out there, the vast majority are written in PyTorch. Bhuvan.
This is a stupid question probably, but you mentioned we don't know what is going on inside the black box. I'm just
NVIDIA's black box, yeah.
or just in general neural network.
In neural networks, yeah.
Works, right? So just curious as to like what makes it so difficult to comprehend what is going on, given that we have all this scientific knowledge around us.
Yeah, Bhuvan, you asked a deep question, which has nothing to do with NVIDIA and the hardware thing, but it is about neural networks itself. Why have neural networks become a black box? Ultimately, as we learned in the last 3 sessions, a neural network is nothing but a bunch of linear transforms followed by an activation function, a deformation function. Does that ring a bell, guys? That's what we learned, isn't it? So what makes it complicated? See, what makes it complicated is the wiring between all these neurons. And when you do the wiring, you end up with trillions of wires, billions and trillions of wires. And each of the wire has a certain strength. If you think of it, each of the wires, think of it in a way, sort of a visceral or intuitive way, as having a certain resistance. If you think of them as resistors, right? And a giant electrical circuitry, they have certain resistance there. Right? Now, the resistances are malleable. You know, it's things like a variable resistor, the example that I gave you, that as you train the neural network, you're dialing in the resistance for each of those wires. Now, how much they learn optimally as you backdrop, as you learn today's technology, well, basically through gradient descent, what values they pick. We know why they are picking the value, because by gradient descent, by calculus, that is the best way they can. They're each seeking the local optimal. Each one of them is optimizing itself with respect to the loss, isn't it? But having said that, at the end of it, why is it that this neuron is practically quiet and this neuron is very active? Right? So that brings in the whole problem of complex systems. There is a paper that was written, I mean, I'll give you a physicist's argument. Right? There was a paper that came out in the 1970, early 1970 or 72. I would like to say 1970. It said, more is different. Right. And it introduced the concept of emergent phenomenon. So think about this. When you heat up water, when water evaporates, we don't know what's going on. It has achieved an energy that is enough for it to escape. It becomes a gaseous state, isn't it? We do understand. You boil a kettle of water, you'll see steam rise out of it. And we perfectly understand it. But boil the ocean, which the sun does every day, and you end up with clouds. Right? Do you see how more is different? Now, if you from pure statistical mechanics, it is not that easy to infer that in sufficiently large quantity, when water evaporates, it will rise up in the atmosphere and form the clouds. It's an emergent phenomenon. Right? It is not so easy to show. I mean, in post hoc, you say, okay, now I know why it happened, but it's rather hard to show why. But when that same cloud rains down or sort of falls upon a cold, a low temperature region in winter, it forms snowflakes, beautiful snowflakes, crystalline fractal shapes. Right? It is not that obvious to see that it will do that. In fact, if in your refrigerator, do you notice that your refrigerator never makes snow? Does anybody's refrigerator make snow? Now, what does it make? Ice, right? It is extraordinarily hard actually to make ice on Earth, snow on Earth, right? It only happens at the high altitudes, right? And so there are a lot of things in life that are emergent phenomena, right? We ourselves may be an emergent phenomenon, right? So what happens is, as you increase the complexity of things, very simple ideas, when you scale it up, you start the emergence, slow emergence of behaviors, complex behaviors that are unanticipated, right? That come about. And it's a lot harder to explain from a reductionist perspective, saying, hey, I understand what each neuron is doing, therefore I understand what the whole network is doing. It doesn't work like that. Right? So, for example, we understand how exactly atoms and molecules work. We have quantum physics at our disposal. It still doesn't explain how people think and behave. In fact, most people are a mystery, isn't it? So that's again an example that as complex systems emerge, you can't just explain it from a reductionist perspective. So that's the way I would explain it. Why neural networks are a mystery? Because see, we are building them out of billions of neurons nowadays. And there's a huge debate. Every time we think they only are this, they will end up doing something that you didn't know that they could do. It's quite a mystery, actually. People are not sure. For example, Jeffrey Hinton believes neurons have developed, these big language models, neural networks have developed understanding in a very human sense. They understand, right? The intelligence has evolved to that extent. On the other hand, Jan LeCun of Facebook and Jeffrey Hinton's contemporary and a co-researcher with him on many things, right? Believes the opposite. He believes that neural networks are nothing but stochastic parrots. Now, which of these two interpretations is true? Time will tell. Right? So that hopefully answers your question.
Question.
Yeah.
So you mentioned that PyTorch charts, they're all libraries, frameworks. What exactly constitutes a framework? I'm not sure I completely understand.
A sufficiently large library that helps you execute a whole domain of activity is a framework. Right? So, for example, if I'm just doing regular expression, I would call it a library, Python. Right? But if I'm doing all of neural network in every architecture that I want to build, I can build with it. Then that library is also a framework. Right? Gives you everything that you need. In other words, my definition is it has closure. Everything that the whole set of activities that you can do in that domain is captured by that library. So, any questions, guys, before we start? So today, what I will do is go ahead.
So you said NVIDIA has this CUDA.
CUDA.
So if you were to buy a computer for programming, which way you would go? NVIDIA and Linux, Windows, or Mac?
My answer is very clear. Every single room that you see here has a Linux with a CUDA, with the NVIDIA GPU.
Okay.
But there is no Mac on premise, except what you guys bring. Right? So that hopefully answers it. So I'll give you a practical reason. See,
Mac is also BS2.
yeah. So the kind of power that you have with NVIDIA's 4090 is practically, it is completely unmatched. Right? Now, Intel and Apple both are trying to enter at the low end. Intel just made a big announcement today, recently. I think today they made a big announcement that they are coming out with processors onto which I think what is it called Gaudi, onto which you can run these large language models. They are in catch-up mode. Apple has this ARM-based processors of their own that they call Metal, right? In which they are throwing in neural cores. If you look at it, they'll proudly tell you that you can get 48 neural cores, 64 neural cores, or whatever it is. Or how many such parallel compute units are there in NVIDIA? 4090, for example. Make a guess. 80. Actually, it has 18, between 18 and 19,000
18 and 19,000 what?
cores,
Oh,
parallel processing cores. Right? So you can imagine the scale at which AI operates. And 4090 is the only consumer, I mean, you and I can only afford 4090. Right? Whereas their state of the art is H200, which will cost you a measly 40,000-50,000 per card. And you'll want to probably put 8 or 16 of them in a server. Right? So you'll have to pretty much sell your house to get a server. That's a current reality, right? And they're about to next week or I think pretty soon, announce yet another next generation thing. So what is happening is they're really at the frontiers of technology. Why are they so far ahead? What happened is when the computer vision movement started, like in 2014, people realized that they used to make these graphic cards for gamers and for ray tracing and 3D design, automobile design and whatnot, and movie making and so forth. The AI community latched onto that and realized we can use this, and they were using AMD also, but they realized that they could use this for AI. Then AMD or other guys didn't catch on to this. NVIDIA's great genius is that they realized that AI market is going to explode. They said, all right, let's reorient ourselves to be people who take the AI market seriously, and let's create cores, let's create chips dedicated to AI processing. So they made that decision way back in 2014. Other people are catching up. They just got into the game a couple of years ago. So they have a huge lead. On the other hand, so that's an argument in favor of having a Linux with NVIDIA. Every single researcher sits with that. It's a very standard setup. Linux, NVIDIA, like 4090. 4090 is what you can afford. And if you have a rich boss, then of course A6000s and fancier A100s or H100s on your server. But desktops are all 4090. Now, the counter argument is that everybody has Mac. And if you have a good enough Mac, especially M2 or M3 Mac stores, you can get by running these models. It just takes a little longer, much longer, actually much longer, but still it runs on those machines quite well. And Apple is investing a lot of energy to catch up. There is a rumor that when in the middle of this year, they're going to come, or I don't know, and Apple is going to release the Studio, M3 Studio. And the M3 Studio will become a pretty viable development station for AI. Right? So the advantage of having Mac is, of course, you do all your other work also on Mac. Right? So that's sort of the trade.
Asif, one question. Where does Julia fall into the spectrum of languages?
Julia, very good question. See, Julia is a wonderful language that was dedicated for numerical computing. Its great virtue is that you don't do this. See, with Python, what happens is you think you're writing in Python, you're not. The Python code gets translated to the C++ layer. Python is just the linking or binding on top of C++, right? And that C++ further gets transpiled onto CUDA, right? And so all sorts of funny things happen along the way. Julia's main premise was that why can't we create a dedicated language for computations, which has the expressiveness, is very expressive and modern, but has the native speed of Fortran and C. And that's the strength of Julia. Julia has been there for quite some time. The trouble with Julia has been, like, people love Julia. I love Julia. And in particular, I love the fact that it was the first language in which I used Greek letters for my variables. And those of you who are mathematician, you know that what is math without Greek letters? Right? So you litter your code with Greek letters. It just feels very natural to do computations when your code and your math look nearly identical because of that. Python has just now developed that ability fairly recently, I think. But It's a beautiful language. It's different. People have to learn one more language. The same reason that R as a language didn't take off. And I mean, it did take off, but it did not gain adoption with the younger crowd. Is the same reason Julia is not getting adoption. Namely, all universities are teaching kids Python. So Python is the only language they know. And so so Python, with all its weaknesses, is here to stay, at least for the short term. All right, folks, any other questions?
You added that Rust also is working.
Oh, Rust is an amazing language. So one interesting development that has come about is a language has come about called Rust that's taking the world by storm. The Linux kernel is completely written in C. Linux tools wouldn't allow any other thing inside the kernel. And yet he made an exception for Rust. Now, a lot of the Linux, increasingly, quite a few modules for Linux kernel itself is coming through in Rust. The reason for Rust is an extremely strict language. It's very difficult to have memory, like to have security holes when you write in Rust. So the thing with that is that people realize that Python, is easy to use, but it has to have a binding to C++. But let's replace C++ with Rust, right? And write the new things with Rust. So those of you who are attending the bootcamp also know that we talked about Qdrint. Qdrint is actually written in Rust. A lot of the new libraries that are coming out is written in this. Hugging Face is completely moving to Rust. So there is a huge migration for those people who are very systems level, very let's build the things foundationally people. They are redoing things in Rust. So Rust, if anything, is not rusty. It's very much shining at this moment with a pretty high adoption curve. In fact, if you come to the Saturday boot camp, the LLM2, you will see that we will make you do some of the exercises in Rust.
And it has the same amount of libraries which are being developed from others for the same amount of
No. The ecosystem is getting bigger. It's getting bigger. Remember Python, Java, these are ancient languages. Right? So the amount of tooling, the amount of everything is unparalleled. So that's that. All right, guys. So with that, I'll take a break. Our first topic today, after this introduction, will be back propagation while your minds are still fresh. Right? But before I do that, does anybody feel the need for a refresher on a gradient descent? We know what gradient descent is, right? We did it in considerable detail. So I'm inclined not to repeat it, but to use the time wisely. All right. So what I'll do is I'll stop this video streaming because this sort of was a back filling of what we are going to do, and I'll start another